QuantSpeak, expert insights from quants for quants.
Welcome to QuantSpeak, a new podcast from the CQF Institute at Fitch Learning.
Hi, I'm Dan Tudball, editor of Wilmot Magazine, and this is QuantSpeak. Myopia. I suffer from it. Maybe you do too. If not, maybe your trading strategy does. Our guest today, Samit Ahlawat, suggests that trading strategy design is fated to short-sightedness thanks to the dominance of static rules-based approaches. The corrective lens for this could well be increasingly sophisticated AI algorithms replacing human judgment in portfolio management, not just for the short term, but over longer holding periods. Samit is a Senior Vice President in Quantitative Research, Capital Modeling at JP Morgan Chase in New York. His CQF Institute talk presents two methodologies for building smart trading strategies. The first, utilizing hidden Markov models, and the second, based on reinforcement learning. Welcome, Samit.
Hello, nice to be with you.
Thanks very much for coming along today. So, first question for you is, what should researchers prioritize when using artificial intelligence and machine learning in building automated trading strategies?
I would recommend three guidelines that must always be kept in mind by researchers. The first and foremost is during the training process, one must avoid information leakage. And there are subtle ways in which information leaks, particularly in financial applications. Let me give you a few examples, and I think that will illustrate, what guidelines every researcher must keep in mind in order to avoid information leakage. For example, during the training process, we often use averages over historic periods. One must always pay careful attention that that historical period does not overlap with the prediction or the testing period. For example, if one is using the previous 5 weeks or 1 month moving average, that data must not include the day on which the trading strategy is traded. So if it is on the day T, all the training must cease or must only use the data available until T-1, the close of T-1. The other thing to keep in mind is that we often use accounting data in finance, for example, P by E ratios. However, the accounting data and the financial data are only released quarterly. So whenever one is using a combination of that, the accounting data and the daily trading data, for example, to construct P by E ratios, the accounting side of the ledger must always refer to the most current available data, which would be corresponding to the last quarter. Historically, one might get an impression that, why don't I use the most recent or the next quarter data? That has to be avoided, because that will lead to information leakage. The other thing that I think is a recurring aspect in finance is the survivorship bias. So for example, when a researcher wants to look at a portfolio of stocks, he or she would look at the data that is available. For example, in an S&P 500, they would look at which stocks are available, have the available data for a testing period, and they would only look at those stocks. There is a survivorship bias inherent in this assumption, because you would only look at the surviving companies that have data available for the entire period. But what about the companies, for example, that went bankrupt or that could not make it through the entire period? So basically then that strategy would only focus on the survivors, and thereby its performance might be skewed to the more successful companies. There are methods to avoid it. For example, if one is looking at a strategy that is generic enough and that is applicable across the board, or is looking at some other indices that are, that are comprised of very large companies, or if the testing set is not is not too big in terms of history. One might make an assumption that the survivorship bias is not prominent. However, it is very difficult to avoid this bias just because the data is not available. So one must always be careful of that. Then I would like to stress the data snooping dangers and the subtle ways in which this can creep into your research. For example, in the hyperparameter selection phase, that is the backbone of any successful AI strategy. And the researcher always looks at the testing and then concludes, whether that hyperparameter is good or not. Repeated phases of this training and testing make the hyperparameter selection learn data from the actual testing phase. So basically, what one must do is have a clear separation between testing, training, and perhaps introduce an additional cross-validation data, which might be used for hyperparameter selection. But once those hyperparameters are selected, they should avoid the tendency to go back and forth, between testing and training in order to perfect the hyperparameters. Because what that step essentially would do is it would learn the training data, and then in the testing phase, the information will leak from the testing phase into the training phase. The second thing I would like to stress is the use of parsimonious models. So in finance, data is finite. We do not have infinite data. And many of the deep neural networks can have thousands of parameters. If we are not careful, what the model would do is it'll overfit, because it has an overabundance of parameters, it can fit all the idiosyncrasies of the data. What we might get is a fantastic performance in the testing stage, but in the training stage. But when it goes into the testing stage, the performance is not stellar because it has just learned all the noise and it does not generalize very well. Then I think understanding what features are being used in the model is critical. We often use dimensionality reduction. However, again, one must always use the processes of reducing the dimension strictly on the training data and make sure that once those parameters are selected, one does not go back, into the testing phase and then try to see whether those assumptions are valid, and if they are not valid, try to again change them based off of the testing performance. That can lead to leakage. And then finally, I would like to stress the choice of modeling methodology. Now, there is a full spectrum of methods available for modeling financial processes, and one must pay careful attention to whether one is choosing a state space model or a model-free method. So state space models typically are trained using supervised learning, whereas if one just wants to focus on an objective function, for example, maximizing the returns without really paying close regard or modeling attention towards the internal states, one might be better off using a model-free method such as an unsupervised learning. But there are pros and cons of it, and this paper explores many of those when applied to building a trading strategy.
The production process is not a trivial thing when you're trying to deploy as quickly as possible. Can you walk us through that?
Sure, absolutely. So production process is a critical component of model development. Once model has been developed, it has to be deployed. So the first guideline that I suggest is to keep the model pipeline clean and intuitive. So the full process of model development, which includes feature selection and model building and initial calibration, all the way across to deployment, and then moving on from that, testing and making sure that the model is recalibrated, and then validating the assumptions. One has to make sure that this entire process is clearly spelled out before the process is deployed, and not as a reaction to some event such as the model not performing according to expectations, and then this process is being revised. So it should be clearly thought of beforehand. The second suggestion is to document assumptions inherent in the modeling methodology. So if the model assumes certain relations between variables as holding, or just makes some back of the envelope assumption around certain features being less than another feature, or perhaps the variable that is being modeled has a correlation or depends in a certain way on another feature, all of those assumptions must be documented and they must be tested. So on an ongoing basis, when the model has been deployed, one must have tools to test those assumptions. And if those assumptions are not true, it is a serious reminder that the model is probably not performing according to the expectations that were inherent when it was being developed, and that something needs to be done to fix those assumptions. The third thing I would like to point out is to validate these assumptions on a regular basis and to recalibrate the model. So every single model has parameters that need to be recalibrated. This recalibration process can be a part of the model itself. For example, if the model is learning dynamically as new data becomes available, it can retrain itself. And in this paper, the model that I have used is being retrained. However, as I stressed out earlier, one must always make sure that the data is strictly historical. And in a production environment, that will be the case because the future data is not available. But one must always be careful about that. So in a nutshell, basically that is the entire production process. So to make sure that the pipeline is clean, all the assumptions are documented, they are validated on an ongoing basis, and then recalibrating the model. Once that is done, the model should be in a good shape.
Now, your paper, using hidden Markov models and reinforcement learning for building smarter trading strategies, was published in the January 2022 issue of Wilmot magazine. Brief plug there for my other employer. Can you give a brief overview?
I would be happy to. So this paper explores the strength and weaknesses of two artificial intelligence machine learning based trading strategies against established trading strategies based on static trading rules. So it delves into how these two artificial intelligence methods, and I have chosen them to cover kind of like a broad spectrum of the AI ML tools. So the first one is hidden Markov models, and the second one is reinforcement learning, which does not use internal hidden states. So these two models are then compared against established trading strategies, and I have picked up three of those, which are basically the cornerstone of most trading strategies. The first one is a moving average crossover strategy, where I use an exponentially weighted moving average of a short-term average and its overlap and crossing or falling below a long-term moving average as a signal for buy or sell. Then I use the very well-known buy and hold strategy because it holds down the transaction costs. And then on the portfolio trading side, I use a price-based momentum trading strategy that uses the prior 6 months to sort portfolios into quintiles, and then it constructs a long-short portfolio based off of that performance, and then holds it for 6 months to see how it performs. And I use these two trading strategies to determine what should be the optimal holding period of that portfolio. So these three established trading strategies are then compared against a hidden Markov model and reinforcement learning based strategies, and their performance are contrasted. And it really provides a guideline of when these two models should be used and when they should not be used. And if they are being used, what are the considerations that a researcher must keep in mind?
You know, career development is of major interest to many of our listeners. And it would be great to get some insight from you on your own path in quantitative finance and machine learning. What was it that brought you to finance in the first place?
It was my interest on quantitative modeling. At the outset, I wanted to build models and use the statistical and quantitative tools that I had learned in my master's degree to have an impact at work where I am using those skills. So that led me to explore the financial industry and get my job here. And once I started developing the models, it opened a whole new world of interdisciplinary research where one has to be aware not just of the modeling tools and methodologies, but also the finance and the terminologies inherent in those, how the real world data interacts, and
Sure.
many of the features that are unique to financial data. For example, we do not have a lot of data. We only have a very limited amount of historical data. And then many of the pieces of data are available at different granularities. Some of them are not available for quarters, others are available practically every second, and still others are available on a daily basis. So there's a whole range of availability of data. And how do we design models that are not only intuitive, but that function well and that can be maintained easily in this framework? That was very challenging to me. And because it involves a lot of interdisciplinary research between model building, between computer science, between finance, it pulled me in. And once I was working alongside with a lot of like-minded researchers, it is a process that strengthens itself. And when the team is working on firing on all cylinders, it just is a great asset. So that's what got me involved in this, and it keeps me going on today.
Right. When was it that you got into finance? What year was that?
I got into finance in 2010. So just about after the Great Recession, we were emerging out of the Great Recession. That's when I joined finance. I think it was a good time. It was a very challenging time. We were not very sure where the financial markets were headed. Investors are making all sorts of bets around, mortgage-backed securities. They would come back. Some were thinking they would not come back. Some were thinking the downturn would continue. But it was a very challenging period in the financial industry, when I joined.
Absolutely. That was an interesting period. And what's interesting about that period as well is as you started to look at employing machine learning methods and so on, was there initially any sort of pushback? Because as I recall, when machine learning first became a discussion point in finance, there were quite a lot of people in the industry who were saying they were perfectly happy with their partial differential equations and didn't see the point. Did you ever come across that sort of attitude?
Yes, I come across that quite frequently. And I think the primary reason why people believe that is because machine learning algorithms are frequently not very properly understood, at least at an intuitive level, just because they are such a complex machinery of processes that we can throw in practically any process and have them model it to a very good degree. And because they are not tailored to any specific process, they lack that intuitive sense. For example, if I were to ask someone to build a model for predicting a probability of default, almost the de facto standard would be to go to a logistic regression or some other regression. Or if I'm asking to build a loss given default method or model, one would think of building a two-bit regression because, the loss given default values are censored at 0. But when we think of modeling a generic process, through neural networks, there is not a special guideline or an intuitive way to think about it. It's just such a powerful machinery that it can model a full universe of processes and do it very well. So when people who have not worked with artificial intelligence encounter this model, there's often a tendency to think that how does it really work under the hood? And if it is giving such a good performance in the training data, will that performance hold in the testing period, in the prediction period, particularly when I know so little about the model? So it's that hesitation that leads them to instead go towards statistical models that are better understood at a more process level, how the equations are working. But really, once one understands how the equations are working in the neural network side of things and how the model is being trained, one can get a lot more comfortable with how it should work well in the prediction phase as well. But I got that pushback a lot, in the initial phases, particularly, there was a tendency to use the more statistical models because they had been adopted and they had been used for such a long time. And just the initial displacement of those from the modeling side of the things was to highlight what are the advantages that the neural network brings to the table that are not offered by the traditional methodologies. And really the foremost ones were it does not require as frequent recalibration. The recalibration process can itself be made a part of that, the neural network itself and its performance. It's really, that's out of sample performance is what make them stand out. And now we are seeing greater adoption of that methodology in finance.
Where's your research taking you next? Are you still going to be looking at fine-tuning what you present in terms of smarter trading strategies, or is your research taking you elsewhere?
Yes, I would say it's taking me to both of those places. So I would be fine-tuning this particular algorithm to look at some of the other advanced machine learning algorithms that are coming up. So this is an actor-critic method that I have used here. One of the suggestions that I had or that I wanted to implement was to use a policy learning directly. An actor-critic uses an actor which learns the policy, and it uses a critic which learns the value function. And the value function is used inside the policy. Now, because it's a two-step process, because these two, actor and critic, are interacting, it can sometimes slow down the process of learning. There is a method, the policy gradient. Using that policy gradient, I can directly train the policy without having to use the critic. However, there are pros and cons of it. So on the next step, I would like to use some of the methods of optimizing that policy learning and directly use a policy learning algorithm and see how it performs in this framework of trading strategy building. The other part of research that I wanted to look at, using a different methodology, was to see how some of the newer methods around generative modeling that are emerging in artificial intelligence can help us overcome this problem of data paucity, data scarcity that I remarked earlier in finance. So for example, in finance, if I were to ask someone to see how a model would perform in a very different environment, in a market environment, for example, in a stagflation environment that has high unemployment and high interest rates, one could always pull up a historical piece of experience. But if I were to combine these features in ways that have not been reproduced historically, for example, if I ask them to see how this strategy would perform in an era where rates are rising and the employment is also rising, and the energy prices are also rising, one will not be able to find out a very sustained period of historical data that replicates these conditions. So the generative models allow us to learn these complex correlations between the variables from a historical basis and to model their probability distribution. And then we can sample from that probability distribution to construct pretty much, the scenario that we want to construct. And that may help us overcome this problem of data unavailability in finance. So I would be looking at aspects of those applications of artificial intelligence.
We're looking forward to seeing that research as you publish it, hopefully with Wilmot. And thank you so much for your time today.
Thank you, Dan.
And for CQF Institute members, you can catch Samit Ahlawat's free online talk, Reinforcement Learning and Hidden Markov Model-Based Smart Trading Strategies. And as I mentioned, it's free, so you've got no excuse. Thanks very much.
Thank you for listening to QuantSpeak. Don't forget to subscribe and do sign up to the CQF Institute for more insights into quant finance.